We've been talking about orthonormal vectors, and now we want to transition to talking about eigenvectors, because eigenvectors, like orthonormal vectors, are vectors that are often convenient to use as a basis for a subspace. So eigenvectors are special, just like orthonormal vectors are special. So the first thing we want to do is define eigenvalue and eigenvector. And the idea here is that if we're given some transformation, so let's say we have a transformation T that transforms vectors v, then normally, since that's a linear transformation, we could write this as the matrix vector product AV, where A is the transformation matrix. But an eigenvector is a vector that satisfies this equation. We take the transformation T of the vector v, and the vector satisfies this lambda times v equation. And lambda is just a constant. So what this really tells us is that if we imagine what normally happens when we multiply by the transformation matrix A, we start with some vector v, we multiply by that transformation matrix, and of course it's going to transform the vector v into some other vector, which we call the transformation of v. And A can totally change the direction of v, it can change the length of v, but it's transforming it in some way. Here, with this equation, this lambda value is a constant, which means it acts like a scalar on the vector. So any vector that satisfies this equation, when the transformation is applied, this value here is just going to scale up or scale down the vector, so it might make it longer or shorter, or if this is a negative value, it would flip it in exactly the opposite direction. But either way, the vector v is going to remain along the same line. It's going to stay parallel with where it started, so it is going to stay in the same direction, and this lambda value is just going to act like a scalar. So the eigenvectors of a transformation are the vectors that satisfy this equation. In other words, you can think about the eigenvectors as the vectors that remain pointing in the same direction, even when the transformation T is applied. So just to take a simple example, let's say that we have a two-dimensional space like this, and let's say that our transformation, we don't know exactly what it does, but let's say our transformation is flipping vectors over the x-axis. So if we had some vector, and maybe it looks like this to begin with, under the transformation, it might look something like this. I'm trying to draw a perfect mirror image of this vector over the x-axis. So this is what happens to the vector under the transformation T. And every vector that we have in 2D space, let's say we have this vector here, it's going to get flipped over the x-axis and become this vector after the transformation. So the transformation is doing that to every vector. Well, as you can imagine, if we have a vector that's sitting right here along the x-axis, under the transformation T, it's not going anywhere. It's not going to flip its direction, because flipping it over the x-axis, when it's right along the x-axis, it's going to stay right where it is, and after the transformation, it's going to point in the same direction. That is an example of an eigenvector. It'll remain pointing in the same direction, unlike these other vectors, which this one points way up here, this one points way down here, this one points here, and it points here after the transformation. The eigenvector remains pointing in the same direction. That's why it's an eigenvector. It might just get scaled up or down by this constant value lambda, which, by the way, this lambda value is called the eigenvalue that's associated with the eigenvector v. But this is the eigenvector, and this lambda value is the eigenvalue that tells us how much the eigenvector gets scaled up or scaled down. Now keep in mind here, when we're talking about this transformation T, it's a linear transformation, so of course it can still be written as A times the vector v. So because both of these values, A times the vector v and lambda times the vector v, are both equal to the transformation of v, we can set those two things equal to each other. So we can say A times the vector v is equal to lambda times the vector v. So any vector that satisfies this equation will be an eigenvector. And we can rework this a little bit. So if we subtract AV from both sides, we can say the zero vector is equal to lambda times the vector v minus the matrix A times the vector v. And then what we can say is that we can multiply this vector v by the identity matrix. We're just doing some algebraic reworking here because the identity matrix doesn't affect the value, so multiplying by it doesn't change anything. So we could go ahead and just do some fancy algebra in here and insert this identity matrix. So we have the identity matrix I and then minus a vector v. And the reason that we did that now is because we have a matrix times a vector minus a matrix times a vector. And we know from the properties of matrices that we can now sort of apply the distributive property in reverse and factor out this v. So this is the same thing as writing lambda times the identity matrix minus the matrix A times the vector v. Of course, if we think about this value here in the parentheses, lambda times the identity matrix minus the matrix A, this is just going to simplify down into one single matrix because lambda is acting like a scalar being multiplied by a matrix here. So that's going to simplify into a matrix. And then a matrix minus a matrix, I'm still going to have a matrix. So if we rename this value, let's say we call it the matrix B, then we could rewrite this as B times the vector V is equal to the zero vector. And notice now that this looks like a null space equation. Whenever we have some matrix times a vector equal to the zero vector, we know that any vector v that satisfies this equation is going to be in the null space of B. Now remember, when we're talking about the null space, we're interested in whether the null space just includes the zero vector only, or other vectors besides the zero vector. Well, in this case, with eigenvectors, we're only interested in eigenvectors that are non-zero. Because if you think about the zero vector as an eigenvector, going back to our picture here, whenever you apply a transformation to the zero vector, it's still just always going to remain the zero vector. So regardless of the transformation that you're doing, any zero vector is just going to stay the zero vector. So even though technically you could say that the zero vector is an eigenvector because it doesn't change its direction, it doesn't really give us any interesting information. It's not helpful. That's just always there. So we're really only interested in non-zero vectors for the vector v as eigenvectors. So we're going to say that we're only looking at vectors v that are not the zero vector. And if there's a vector that is not the zero vector that satisfies this, then that tells us that there's going to be a non-zero vector inside the null space of B, which tells us that the matrix B, or this matrix here, is going to have linearly dependent columns, and it's going to tell us that B is not invertible. And therefore, if B is not invertible, we know that the determinant of B has to be 0. So the determinant of B is going to be 0, which means that we can say that this equation up here is only going to be true for non-zero vectors V when the determinant of this matrix, so when the determinant of lambda, the identity matrix, minus the matrix A, is equal to 0. When that determinant is 0, we're going to have non-zero eigenvectors. So this right here is really the formula that we're going to use to find our eigenvalues. Then from our eigenvalues, we'll be able to get our eigenvectors. So let's take an example and walk through how we would go about using this equation to find eigenvalues and then eigenvectors. So let's say we're given some transformation, and it's given to us as the matrix vector product, and we have for the matrix 2, -4, -1, -1. So this transformation takes vectors v and applies this transformation matrix, which is the matrix A, to transform those vectors v. So the first thing we need to do is find this value down here, the determinant of this matrix. Well, to find the determinant of this matrix, we'll multiply lambda by the 2 by 2 identity matrix. We'll use the 2 by 2 because A is a 2 by 2 matrix, and then we're subtracting A. So lambda times the identity matrix minus A, so minus A, 2, -4, -1, -1. And then here, we'll multiply lambda as a scalar across the identity matrix. So we'll get here lambda 0, 0, lambda, minus A, 2, -4, -1, -1. And then we'll do the subtraction here. So we'll get lambda minus 2, we'll get 0 minus a -4, 0 minus a -1, and then lambda minus a -1 or lambda plus 1. Now to find this determinant, remember that when you want to find the determinant of a 2 by 2 matrix in the form A, B, C, D, that determinant is equal to A times D minus B times C. So in our case here, that's lambda minus 2 times lambda plus 1 minus 4 times 1. And if we multiply this all out, we get lambda squared plus lambda minus 2 lambda minus 2 and then minus 4. That gives us lambda squared plus lambda minus 2 lambda is a minus lambda, and then minus 2 minus 4 is a minus 6. Now this right here is called the characteristic polynomial. What we then want to do is set this equal to 0. So we'll say lambda squared minus lambda minus 6 equals 0. And this then is called the characteristic equation. And the characteristic equation is what we want to solve for the values of lambda. And in order to do that, we'll need to factor this left-hand side. If we can't factor it, we'll need to either complete the square or use the quadratic formula. But in this case, this polynomial can be factored. So it can be factored as lambda minus 3 times lambda plus 2. And remember that when you have two factors multiplied together set equal to 0, we can set those factors equal to 0 individually. So we can say lambda minus 3 equals 0 and lambda plus 2 equals 0. And then to solve this equation, we'll add 3 to both sides and we'll get lambda equals 3. And to solve this equation, we'll subtract 2 from both sides and get lambda equals negative 2. So these then are our two eigenvalues, the eigenvalues for the matrix A. And one thing you can always do to check your eigenvalues is that up to this point, we haven't yet defined the trace of a matrix. The trace is always equal to the sum of the values along the main diagonal. So in A, the values along the main diagonal are 2 and negative 1. So 2 plus negative 1 is 2 minus 1, or 1. So the trace of A is 1. And the sum of the eigenvalues should always be equal to the trace. And we can see that we have 3 plus negative 2, or 3 minus 2, that's equal to 1. That matches the value of the trace, so that checks out. The other thing is that the determinant of the matrix A should always be equal to the product of the eigenvalues. So by that rule, we would say that the determinant of A should be 3 times a negative 2, or negative 6. So let's check it here. What we should get for the determinant of A, so we'll say the determinant of 2, negative 4, negative 1, negative 1, is equal to 2 times a negative 1 is a negative 2, minus negative 4 times a negative 1 is a positive 4. Negative 2 minus 4 is a negative 6, and that checks out. So the eigenvalues are always related to those two values of the matrix, the trace and the determinant. And then once we get the eigenvalues, what we want to do next is create the eigenspace, or define the eigenspace for each one. So let's start with lambda equals negative 2. First of all, an eigenspace in general is defined for each eigenvalue as the null space of this matrix here, this lambda times the identity matrix minus A. Keep in mind that this lambda times the identity minus A, we found that matrix. It's this matrix right here. So we're saying that the eigenspace for lambda equals negative 2, for example, so the eigenspace for the eigenvalue lambda equals negative 2 is the null space of this matrix when we plug in lambda equals negative 2. So we'll get negative 2 minus 2, that's a negative 4. So negative 4, and then we have 4, 1, and then negative 2 plus 1, that's a negative 1. Now in order to find the null space of this matrix, we can just go ahead and augment it with the 0 vector and then put it into reduced row echelon form. So we would have negative 4, 4, and then over here 0. But let's go ahead and divide through the first row by negative 4 to get a 1 here. So we get a positive 1, we get a negative 1, and then we would move on to the second row. For the second row here, let's subtract the first row from the second row. So we'll say 1 minus 1 is 0, and then -1 minus -1 is a -1 plus 1, or 0. So already we have our matrix in reduced row echelon form. Remember that these columns represent v1 and v2, the components of the eigenvector v. If we pull this back out into a system of equations, we get 1 times v1 minus 1 times v2 is equal to 0. The bottom row doesn't give us any information, it just says 0 equals 0. So we only are working with this equation, and if we go ahead and solve for the pivot variable v1 by adding v2 to both sides, we get v1 equals v2. And then if we make the substitution, so we'll make this substitution v2 equals t, then we can say that our solution here is v1, v2 is equal to t times v1 is equal to v2, but we made the substitution v2 is equal to t, so v1 is equal to t, so we would say v1 is equal to 1t, and we said v2 is equal to t, so we would get a 1 here as well, which means that this eigenspace e -2 is defined as the span of this eigenvector. So 1, 1 is an eigenvector for the matrix A, and the eigenspace e -2, where lambda is -2, is defined as the span of this vector. Now we need to do the same thing with lambda equals 3. So we'll say the eigenspace for lambda equals 3 is the null space of this matrix when we plug in lambda equals 3. So 3 minus 2 is 1. We get 4, 1, and then 3 plus 1 is 4. Now we need to go ahead and augment this matrix with the 0 vector and then put it into reduced row echelon form. But when we do that, notice here that we'll get 1, 4, and then augment it with the 0 vector. If we then subtract the first row from the second row, we get 1 minus 1 is 0, 4 minus 4 is 0, and then we would get 0 minus 0 is 0, and we're already in reduced row echelon form. And if we pull out a system of equations, we just have v1 plus 4v2 equals 0. We solve for the pivot variable and we get v1 equals -4v2. If we then again substitute v2 equals t, what we can say is that the solution v1, v2 is going to be t times, we said v1 was equal to -4v2. Well, v2 is t, so v1 is -4t, so we can put a -4. And then we said v2 is equal to t, or 1t, so v2 is 1t. And so then we can say that the eigenspace for lambda equals 3 is going to be equal to the span of this eigenvector, this is the other eigenvector, -4, 1. So what this really tells us then is that we have two eigenspaces. First of all, we have two eigenvectors. We have the vector 1, 1 and the vector -4, 1. And if we sketch those out, we can actually sketch out the eigenspaces. So think about two-dimensional space here. And we'll go ahead and sketch in 1, 2, 3, 4, 1, 2, 3, 4, and then 1, 2, 3, 4, something like that. So if we have the vector 1, 1, we could sketch that in like this. It would look something like this. And we're saying that the eigenspace for lambda is -2 is the span of that vector. Well, the span of that vector is just going to be the line through this vector. So it might look something like this. And if we extend it this way as well, it might look something like this. So this entire line here, this is the eigenspace for lambda is -2. And then the eigenspace for lambda is 3 goes through the vector -4, 1. So let's sketch in -4, 1. That would look something like this. So -4 and 1, maybe like that. And then that means that the eigenspace is the span of this vector, which means it's going to be all the scalar multiples. It's going to be the line through this vector. So it might look something like that. And then out this way as well. And so this is the eigenspace for lambda equals 3. And so we have our two eigenspaces. And then the other thing that we know is that because along this eigenspace here, lambda is -2, what that tells us is that every vector along this line, every vector anywhere along this line, when we apply the transformation t, it's going to get flipped around in exactly the opposite direction and scaled by 2. So instead of maybe this vector here that we're showing, the vector 1, 1, that would get transformed to the vector -2, -2. So it might look something like this after the transformation, because it gets doubled in length and flipped around in exactly the opposite direction, but it stays along the same line. It's parallel, it's collinear, so it's an eigenvector. And then any vector along this eigenspace for lambda equals 3, we know that the vector is going to get scaled up by a factor of 3. So if the vector looks like this, we triple it in length and it still points out in the same direction. If we had, though, a vector along this line that maybe looked something like this, so let's say the vector is that short, it looks like that, it would get tripled in length and go in the same direction. So we would maybe triple it in length, maybe that's double, and maybe that's triple, something like that, and it would get scaled up to here. So that's what these really tell you. Once we have the eigenvalues, we can use them to find the associated eigenvectors, and then those eigenvectors give us the eigenspace, and we can see what's actually happening to the vectors in those eigenspaces.